asks us to draw a picture of the atom that shows where the protons, neutrons, and electrons are for carbon 6. Oh, yeah, so that's the first thing I will say. I'm going to fix that though. It should say carbon 12, although you could do carbon 6, but I want to answer this question as carbon 12. So use a small open unfilled circle for a proton, a small filled circle for a neutron, and electron, E minus for each electron. Of course, the nucleus will appear much larger in your picture than it really is, but that's okay. So the idea behind this question is just to get an idea of what an atom really looks like, or even though it's much too small for us to see. And in the lecture notes, what I did is I drew a picture with a circle in it, and I said, if you go to the very center and you draw a tiny, tiny dot, and if you can see that, then it is much larger than it's supposed to be, because the nucleus is a very, very tiny portion of the atom. And around it are all of the electrons, and inside of the nucleus are the protons and neutrons. And so let me go through this. So this is carbon 12. And carbon 12, because it's carbon on the periodic table is box number 6. And the 6 number, the number above the chemical symbol, is going to be the number of protons for all carbon atoms. So I know it has 6 protons. And carbon 12, so the 12 is the protons plus the neutrons. So 12 minus 6 protons is 6 neutrons. And it says up here that it's an atom of carbon 12, and atoms are neutral, meaning that if to be neutral, you have to have the same number of protons as neutrons. So atom has no charge, and protons equals neutrons. Sorry, protons equals electrons. So we also have 6 electrons. And I'm just using the symbol here, E superscript minus for electrons. And now I'm going to do is I'm going to scatter my electrons around this space. We'll talk more about where in this space the electrons are, but for now, just draw them around the nucleus. And then if you want to, you can draw them moving very fast around the nucleus in random directions. And because, as we will see, that is part of the picture that we will be developing for the atom. And now for the nucleus, of course, to actually draw it, I'm going to draw it bigger than this. And I have 6 protons and 6 neutrons, so you should scatter them in there. So, and I've got 4 neutrons and 3 protons so far. Let's see. One, two, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Something like that. And the exact pattern doesn't matter. They're smushed together really closely, and they're very, very tiny and in the center of the atom. And one of the things I don't ask you about on the homework that is in the online textbook at libretext.com is they talked about how they figured out that the atom is mostly empty space. And that's actually something I'm going to write too. Atom is mostly empty space. Is they shot particles through atoms of gold, and all of the particles went straight through as if there was nothing there, except that every once in a great while, one would actually hit the nucleus and bounce back. And that was part of the evidence, and really a key piece of evidence that the atom was mostly empty space, that the nucleus was very, very tiny, and however, if you hit that nucleus, you were 99.97% of the mass of the atom, and therefore it was like running into a brick wall, and anything that hits it bounces back. So 99.97% mass of atom. So the electrons are in this space, but think of the electrons as tiny feathers moving very fast around the nucleus, that if a particle comes through, the feather moves out of the way. And I don't know if that helps at all, but that's my picture of an atom. And the part that you have to have for this part is the picture right here in black. You don't have to have any of the red stuff, and you don't have to have any of the information down here, as long as you have the right number of particles. Now, if you did a carbon-6 atom, a carbon-6 atom means that it has a mass number of 6, and since it has protons 6, you would have to draw 0 neutrons. So it is a question that can be answered for carbon-6, but carbon-6 is not something we usually think of, and I meant to say something closer to carbon-12 for this problem. So, and I will go in and fix that. Any questions about this problem?
Not really about the problem, just for my own general, knowledge. I've always wondered, and I usually just accept things for what they are, but I've always wondered, how do we know this? Like, have we actually seen this? Or is there some sort of microscope that can actually monitor or get down to the atomic level where we can actually see this with our own eyes, or is it just all a theory?
Right, no, so this is a good question. Hold on.
We can see, bacteria at the microscopic level. I've read that there's even some sort of molecular microscope, but I don't know. Just theory. Just my own general question.
Yeah, no, so good question. I would say that when they discovered this information for the atom, they could not see atoms. They could only do experiments that interacted with atoms and make hypotheses and about what they were seeing. Since then, though, and this has been since about the certainly the 70s, maybe the 60s, they've had things called scanning electron microscopes. That should be a capital E. And scanning tunneling microscopes. And this last one is really starting to see, again, not actual atoms. It is starting to see atoms or evidence of atoms, because you'll be able to scan across a surface and you'll see like bumps. And the bumps will be in the same size as the atom sizes. So are they seeing atoms? Some people would say yes. Some people would say they're saying evidence of atoms. But then if you have something like what's called a benzene molecule, and you scan it across the surface and you see a shape that looks like a hexagon, are you seeing atoms or are you seeing molecules? I would say, I would say yes. You're seeing certainly evidence of molecules. But in science, a lot of stuff is based on our best hypotheses and our best theories. And we've gotten to the point where we're very confident of things based on those theories. So, but this one, I mean, this question is this experiment is a very elegant experiment, because it's called the Rutherford gold foil experiment, and you can read about it, where they took gold foil and they hammered it until it was only a couple atoms thick in the layer, and then they put particles through it And again, the vast majority of the particles went straight through it. I'd say like 19,999 or something went through it out of 20,000. And then that 20,000th particle would slam into the nucleus and bounce back, which they had no idea, they could not see the atoms. They could only see evidence of how the atom worked, which is pretty cool. But of course, we would prefer to see things. I don't know. I think that was Michael. Michael, did that answer your question more or less, or start
I
to?
just always, I'm getting a little off topic, but since I'm paying for this class, I've always wondered, like, how do they say we split the atom and then we got a bomb from doing that? I just don't understand how that works. But you can get back on topic. I'm sorry.
Well, and I'll say one other thing about splitting the atom, which is, so there you know what atoms you have because you can weigh them, again indirectly, and then you can split them, and there are ways of measuring them after you, and the complicated ways, but of measuring what you get and how weighing them after they split as well. But yeah, so and again, we can talk about this in office hours in more detail if you'd like, or if we have time after the homework. But let me stop. But that's all good stuff.